Hello everyone, my name is Santos. This work is entitled Hybridization Effect on the Bending Properties of Flax Composites, and it was a joint collaboration between myself and my colleagues João Parente, Sara Balvez, Marco Silva and Paulo Reis. It is divided in three parts. First, motivation and objectives. Second, experimental procedure and mechanical characterization. Third, results and conclusions. Why is work? Eco-friendly and biodegradable composites are desirable due to the enormous pressure on industry as a result of the air pollution, global warming, and the scarcity of fossil fuels. The use of natural fibers, reinforced polymers, composite, including flax fiber, is interesting because to their low density, abundance, low cost, renewable, no abrasive during processing, and biodegradable. For this purpose, flax fiber bidirectional woven fabrics taffeta with 195 grams per square meter, fiberglass bidirectional woven fabrics taffeta with the same density, and SCR green epoxy 56 resin with an SCR self-clean hardness supplied by Sycomin were used. Three laminate configurations were prepared by a layup technique: laminate with 8 layers flax fibers, laminate with 2 layers of fiberglass on each side and 8 layers of flax fiber in the middle, denominate 1X hybrid, and laminate with 2 layers of fiberglass on each side, 8 layers of flax fiber between this and 2 more layers of fiberglass in the middle of flax fibers, denominate 2X hybrid. The manufacture of laminate consists: Step 1. The epoxy resin were mixed during 10 minutes with the hardness at slow speed and after vacuum applied for another 10 minutes. Step 2. The system has placed inside the vacuum bag and a load of 2.5 kN as applied during 24 hours in order to maintain a constant fiber volume fraction and uniform laminate thickness. During the first 4 hours, the bag remained attached to a vacuum pump to eliminate any air bubbles existing in the composite. Step 3. The procedure as followed according to manufactured datasheet: epoxy resin in an oven at 14 degrees during more 24 hours. Finally, cut the samples to the appropriate dimensions to test. 3-point bending static tests were performed using specimens with the geometry shown in figure and tested with a span of according to the thickness and length of the laminate tested, following to the recommendations of the standard test. Shimatsu Universal Testing Machine equipped with a 10 kN load cell as used, and for edge conditions, at least 5 specimens were tested at room temperature and at a rate of 2 mm per minute. The graphic showed the nominal bending stress versus strain curve results of the static bending tests performed for all laminates. The curve trend is significantly different depending on the type of fibre constituting the composite laminate. Composite laminate with glass fibre showed either shock compared to flax fibre laminate. It can conclude that the glass fibre increases the stiffness of the laminate. When the flexural stress is maximum, fibre breakage occurs, as can be seen in figure. The typical damage in this point. It is possible to observe that with the insertion of fiberglass layers on the outside of the laminate 1x hybrid and also inside 2x hybrid, the maximum value of flexural stress is significantly increases. In terms of bending stiffness, there was an increase when the outer layers of fiberglass were added 1x hybrid, but a decrease compared to the previous one. Then the intermediate layers are introduced 2x hybrid. Finally, with regard to flexural strain, the values decrease to 1 and 2x hybrid. In terms of stress relaxation, tests were also performed with the same equipment at room temperature and with geometry similar to those used of the bending tests. All experimental procedures were supported by standard tests. A fixed strain is applied and the stress accorded in function of time. The strain value used in the different laminates were 0.73%, 0.39% and 0.38% respective to flax 1 and 2x hybrid. From these tests, with a during of 3 hours, 108 minutes, the stress as plotted versus time, and the data are shown in figure in terms of average curves. Behind the average values obtained after 108 minutes, closed round symbol figure also show the respective maximum and minimum value for each condition. Similarly, and for the 2x hybrid laminate, the strain values used were 0.28%, 0.82% and 1.46%, and 108 minutes tests were performed, and the stress is recorded in function of time. From these tests, the stress as plotted versus time and figure presents the results in terms of average curve. To predict the viscoelastic response, several models are presented in bibliography. One of them, widely used in various studies, is based on the model KWW. The KWW model has applied to predict the behavior in a displacement. Step 1, application of the model. Step 2, estimating the model parameters. And finally, application again the model and compare with the average curve. The table summarizes the parameters calculated and estimated by the KWW model for the different study tensions, as well as the theoretical and experimental values of T errors and their errors. We can observe that the errors are generally low. Regarding the creep testings, the tests were carried out in the same machine and with similar samples at room temperature during 108 minutes, where to compare the different laminates a fixed stress as applied of the 15 megapascal and the displacement recorded during the loading time. Figure shows the results in terms of average curves behind the average values obtained after 108 minutes. Closed round symbol. The figures also show the respective maximum and minimum values for each stress. Similarly, and for the 2H hybrid laminate, the stress value applied were 15, 118 and 177 megapascal that correspond 25%, 15% and 75% of the maximum stress, and 108 minutes test were performed. From this test, the displacement as plotted, best time, and figure present the results in terms of average curves. In terms of creep tests, the KW model is applied to predict the behavior in a flexural stress. Step 1. Application of the model. Step 2. Estimate the model parameters. And finally, application again the model and compare with the average curve. In this study, as applied to the Findley law, which is widely used to describe the creep behavior of composite materials. This method of application, the model, is similar to the previous one, and in the graphs it is possible to compare the behavior of two models. The table shows the parameters calculated and estimated by both models for the different study stations, as well as the theoretical and experimental value after 3 hours and their errors. Also, influence the error of the applied models are low. Conclusions. The maximum bending stress increases with that the number of layers of fiberglass are added to the laminate both inside and outside. From the stress relaxation and creep test as evident a decreasing of the stress with time relation to the reinforcement the laminate with glass fiber. In the Laminate 2H hybrid stress relaxation test show that stress decreases over time, which is sharper for each displacement. In terms of creep, the displacement increases with the time, and consequently for which flexural stress are observed with values. The KW equation first with kit across the results obtained for the experimental test, and it can be used to model the effect of stress relaxation and similarly applying Findley's equation to experimental creep results gives a good creep modeling. Thank you for your attention.